Okay, got the recording started. And the share. Okay, excellent. So yeah, again, thank you all for being here. I'm going to start off today with the idea of sustainable intensification. All right, this is an idea that a lot of us here are familiar with. In this department, in this college, we aim to increase agricultural yields without adverse environmental impact and without converting additional agricultural land. So we do this in a few main ways in this college, through crop breeding and genetics to make more resilient and higher yielding crops, through good nutrient stewardship so that we can optimize the use of the applied agricultural inputs, and through integrating new technologies into our agricultural production systems so that we can maybe define the spatial variability of the landscape so that we can optimize both our genetics and our nutrient, our ag inputs, right? And over time, these incremental improvements that we've made to these cropping systems have yielded a lot of improvement to the agricultural industry. I really like this graph, and I've showed it in several of my presentations. This is the total factor productivity of US agriculture production, where we see our agricultural output has increased at about 2% each year, and that actually outpaces the greater economy by about double. So the research and investment that we do in agriculture has added a lot of value, and we should be proud of the fact that we can produce 2.5 times more ag output per input than we were in the late 40s, right? However, negative effects of our intensive cropping systems are very visible when the ground is fallow. In the winter, we drive around and we see ditches that are full of sediment, and in the spring, eroded hilltops dot the landscape. And these soil resources that we rely on have been degraded and lost in a fraction of the time that it took for their formation. And this is an external thing that our research efforts have not really been able to respond to yet. So if you talked to me over the last 5 years, you know that I've been working with Clover. Clover is a cool season perennial legume crop, and it has a robust root and rhizome system that gives it extreme persistence and a lot of spring vigor. So it starts growing right away when the soil and environmental conditions are met. And that extreme persistence under adverse environmental conditions and intensive agricultural management. And this extreme persistence allows us to integrate Clover into our corn cropping systems. And it comes back year after year without the need for reseeding, and we keep hitting it and it keeps coming back, right? And utilizing Clover in this way as a perennial ground cover or a living mulch, we found it can reduce erosion and nitrate leaching by about 70%. So these environmental impacts that our development of the corn systems have not really been able to respond to quite very well. And it also increases biodiversity and primary productivity. However, there still are some barriers and systematic changes that are needed in order to integrate Clover into our Midwestern cropping systems. And these are just a few examples. We have high establishment costs. That is a pretty good barrier for a lot of producers. It's also increased management costs because farmers don't necessarily have the tools and equipment necessary to manage these systems. Another big one is required corn stover removal. And we're able to kind of manage the system because we have so much experience running our experiments, but the management of 2 crops at one time really kind of takes an adaptive approach that our farmers don't have the expertise to necessarily do right away. And so because of those barriers, we might ask, why should we reinvent the wheel, right? We know how to grow corn. We know how to grow it really well. Why should we grow it in a more difficult way? So I came across this S-curve model, and this is really typical in engineering when we're talking about technologies, where this is with investment into new technologies, we see birth, infancy, growth, and maturity. And through the development of these technologies, we get closer to this fundamental limit. that's set by, and in corn cropping systems, that fundamental limit is set by biological, environmental, and economic constraints. And in order to get closer to an ideal system, at some point we can't optimize any further, and improvements might take an evolutionary leap. This leap might take a step back initially, but taking that step could bring us closer to an ideal system through investment. And so that's really how I kind of think about our research, where we're taking these initial steps in order to optimize these cropping systems so that they can compete with our conventional systems. And at some point, maybe we do get closer to an ideal system. So all that to say that erosion is bad, but it also kind of gives us a little bit of insight in how I approach problems and how I prioritize my research. So in 2019, I came to you guys with my thesis, nitrogen management for maize production in a cured clover living mulch. And in this work, I had a few main findings. I did some experiments and found that biomass inputs are readily mineralizable, and we can see nitrogen pools are increased after we manage the living mulch. So we see that in the soil. We also found that cured clover living mulch can provide some or all of the nitrogen requirements for maize, and stover removal can offset some of the increased management costs of these systems. We also came up with several new questions. I was kind of interested at the time in the effects of tillage and row establishment on those biomass nitrogen pools and how that affects the nitrogen cycling. I was also kind of playing in my mind with alternative suppression management treatments. And I was also interested in the spatial and temporal distribution of these nitrogen inputs. I knew that we were getting some from the living mulch system, but I didn't know how or when or where the nitrogen was coming from. So at the end of my thesis, and John talked about this too, they gave me an opportunity to kind of fit more of the puzzle pieces together. And so they allowed me to design my PhD work, design a lot of the experiments, and get to work. So that's what I did. I got to work with the goals to define general relationships between clover and corn in this intercropping system. And I hope to improve nitrogen management recommendations in the cured clover living mulch system. So just kind of a slideshow of all the fun things that happens in 3 years when we undertake these big goals. So today I have my dissertation, management considerations for maize in a cured clover living mulch. So today I'm going to be talking about clover biomass nitrogen inputs in the system. I'm going to provide a little bit more context to that topic through talking about root distributions in the mixed cropping system. And then I'm going to jump over a little bit and talk about sources and drivers of nitrous oxide and emissions, and then finish with a few conclusions and research opportunities. So yeah, clover biomass inputs. I'm going to talk about this graph. I'm going to reference this quite a few times in my presentation. This is a regression equation of clover biomass in the living mulch system. This was in 2020. It's a really good year. We had really high yields and adequate rainfall. And this is the general kind of distribution of clover biomass in this intercropping system. In the early spring, we see a lot of competition, right? We're planting, before mid-May often, and that's also when the clover really takes off. I was talking about those root and rhizome systems, how they really have a flush of growth early in that growing season. And a lot of our management is to kind of hold that clover back so that those maize seedlings can compete early part of the year. So we accomplish spring suppression through a couple different ways. We do our mowing, which deposits, sometimes depending on how much clover is present. We do our mowing, which deposits biomass nitrogen inputs on the row and the interrow zone. We follow that with tillage, which incorporates about 30% of the clover residue, puts that underground. And then later on, we will use broadcast glyphosate herbicide to kind of hold that clover back, allow the corn to grow through that clover canopy and reach the light resources. And after that point, we're good to go. So this is a photo of right next to the row zone after strip tillage. And I know it's a little bit blurry, but I was just digging around and, as I was thinking about this problem of where that biomass is going, what's happening to it after. This is only a few days after strip tillage, and we can already see that really nice, rich mix of low CN residues that break down readily. And it's already starting to break down. It's mixed with that soil and already mineralizing. So following that period, our clover recovers in June, and it reaches about its max biomass between 2,000 and 4,000 kilograms per hectare at this time period. And if we look under the clover canopy, we can really see a lot of partially decayed or dying residue and a lot of biology right at that soil atmosphere interface. Those microbes are going because they have so much biomass inputs and so much substrate to really work on. So it's kind of this dense, humid environment under that clover canopy. And after that point, the corn starts to grow, like I was talking about. It shades over that clover canopy, and then there's not enough light resources for that clover to maintain its biomass, and it begins to decline for the remainder of the growing season. And by the end of the year, the soil surface looks like this, and it's had 3,000-4,000 kilograms per hectare of biomass inputs in this zone. And so there's a lot of partially decayed plant material, and that structure is really strong just from everything working on that and tying everything together. So observing this temporal dynamic over and over again in our experiments, we were wondering where, when, and how much nitrogen is actually coming from these biomass and inputs. So in 2020 and 2021, we were all feeling bad, but I got to work on this experiment, and it was a pretty simple experiment where we used this strip tillage tool and had a couple different nitrogen rates. But what was kind of intensive about it was what we measured. We had a lot of in-season measurements, including clover biomass, soil nitrogen fractions, litter decomposition using litter bags, nitrous oxide emissions, and maize yields at the end of the growing season. And in 2020 and 2021, if you remember, it was kind of dry last year. The weather conditions were very different, right? The purple is 2021. The left graph is growing degree day units and our growing degree days. The right graph is our cumulative precipitation. So yeah, 2020 in purple, 2020 in orange, 2021 in purple. 2020, we had above average growing degree days and quite a bit below average rainfall, especially during this period where the corn just got cooked. So these different environmental conditions during these two growing seasons really impacted the results. This is that same graph that I was showing you earlier. The green is that same clover biomass distribution that I kind of use as my model system. And the orange is what happened in 2021. So we peaked at around the same magnitude at about the same time, but then the clover completely died. It died, and then we had a couple inches of rain and it reached its early season peak towards the end of the growing season. So not really what we planned to have, and not really what we like to see when we're trying to do replicated experiments over years. It also impacted maize yields. We have grain, stover, and plant and uptake, but they tell the same story. We saw very good grain yields in 2020 at our different nitrogen rates. Same story with stover and plant and uptake. And so we can really see that 2021 is kind of complicating the story, right? So I like to think of this as more of a case study than experiment that's really able to describe these general relationships that I'm after. And so I'm going to leave that out for today. Maybe we're relieved for that, because I think that I might drive myself crazy trying to trying to explain all of that, but we're going to leave that out for today. So in 2020, I got to work describing the relationships using targeted sampling methods, litter bags, and in-season biomass sampling. So I had Caitlin here on a weekend, and we were making litter bags right before the planting season. Here I had installed a couple and had some targeted sampling approaches that I used to kind of get after this larger question. So the Clover additions that I factored into my analyses were spring management. So spring management adds Clover biomass inputs. The mowing adds them to the row and interrow zone, and tillage incorporates the mowed and standing clover. And to understand and to quantify how much tillage actually incorporates, we utilize the technique that I found in Ray Almaris's paper. He did a study in 1988, which was also kind of an extreme drought condition. So that was kind of a fun parallel. But basically what he did was put some plastic beads on the surface and then ran over them with tillage tools and excavated them to determine their spatial orientation after tillage, right? So I quantified that our tillage management incorporates about 30% of what's on the surface in the soil profile. Shade suppression also adds a lot of the nitrogen inputs in the system. And so I utilized a regression equation similar to this and quantified the amount of inputs every day, right? This is a simplified version of this, but I basically took the slope of this regression equation for every day and then took that amount of clover biomass and related it to my clover decomposition data that I got from litter bags. I had litter bags at 0, 10, and 20 centimeter depths, and both the buried ones were about the same, and so I combined those equations. But basically, there's a difference in the rate of decomposition between surface and incorporated clover biomass inputs. So I related each of the inputs into their relevant decomposition curve. And by pulling all this together, I came up with this model that could describe our daily mineralized nitrogen in the cured clover system. So we can see this is all of our spring management inputs, or this is all coming from our spring management inputs. It declines until we reach our peak biomass later in the growing season. And then if we remember that biomass curve, it peaked and then it went down. And so those inputs from shade suppression increased our mineralization towards the later part of the growing season. I have this split up between daily mineralized N in the row zone, and in the interrow zone. So our light green is the interrow. And we can see that over in the early part of the year, we only mineralized about 8 kilograms of nitrogen in that row zone because it only occupies kind of a small portion of the total area. And most of those nitrogen inputs are actually in the interrow zone. So we're adding 94 kilograms every year, year after year, to this system. We also measured soil nitrogen. This is soil nitrogen in the row zone, looked at NH4 and NO3, and this is basically what we expect from fertilizer. Ammonium, it starts off up here, and then it's nitrified, and so we see our nitrate peak a little bit later in the growing season before both of them decline from crop and uptake. And then in the interrow, we don't really see much change. There's not a really large magnitude of soil nitrogen in the interrow zone, despite those 86 kilograms of N as biomass inputs. So we do see a little bit in these regressions that nitrogen does increase in the late spring somewhat, and that corresponds with a majority of our nitrogen inputs and slow clover growth, but it's not really at the magnitude that we can quantify, or that we can see the nitrogen that was added through that biomass mineralization in like a mass balance approach, right? And also we saw excellent grain yields in 2020. My max yield was about 238 bushels an acre. So we yielded well in this system, but it required nitrogen. And that goes against what I found in my thesis. where I found that we can replace some or all of our nitrogen inputs by utilizing the Kura system. So to wrap up with this part, and like I said, I'm going to add a little context to this later. We were able to define that spatiotemporal biomass nitrogen input, found that most of it is deposited and mineralized in that interrow zone, over 90%. But there is kind of an unclear fate of those interrow nitrogen inputs. We didn't see it in the soil, and we saw a response in our grain yield to fertilizer nitrogen. So, and we also found that maize does require nitrogen sometimes, and that's probably an interaction with stand history, right? So, but that wasn't something that I was able to, replicate and test over several years to kind of define those relationships. But that's kind of a hypothesis that we can gather from these different results. So maybe if we look underground, we can give that part of the story a little bit of context and try to explain some of these questions that we weren't able to answer. So let's look at our root distribution. This was a fun project that I did in 2019. This was our first idea after the thesis. And I was really thinking about tillage management. We use this rotary zone tillage tool, or we have used it quite a bit in the past. It's a really effective machine that creates a nice clover-free zone and a nice seed bed for planting. So the rotary zone tillage is very effective, but it has a really high cost due to limited working widths and limited working speed. It's a PTO-driven tool that requires a lot of horsepower to run this. So, and it's also a custom-made tool, so it's not really accessible to most of our farmers. So I was really looking towards an alternative to the rotary zone tillage tool. We had an Orthman, a shank strip tillage tool that was sitting in our shop, or in the shed, that we had put away for a few years because there was a project by Michelle Dobretz that was conducted before I entered the department. And she tested the shank strip tillage tool against the rotary zone tillage tool and found that rotary zone tillage increases yield because it speeds maize seedling development. But I knew that the strip tillage tool was more commonly available, had a lower cost, and can integrate banded herbicides. So I figured, well, we can reduce costs by utilizing this cheaper machine to run, and we can reduce the amount of field passes by doing essential management practices in one pass versus two. At the same time, I was thinking about anhydrous ammonia a lot. Rod and I were talking about anhydrous in some other contexts about nitrous oxide emissions and how it creates this caustic soil zone after application. So we apply anhydrous ammonia, and it rapidly hydrolyzes with the available moisture in the soil. And the resulting products of that reaction are ammonium salt, which can increase our osmotic potential above 1 MPa. So that sucks a lot of the water out of everything surrounding it. And we also are left with a hydroxide ion, which increases our pH to about 9. And so this is an environment where most soil biota are not comfortable living with. So it kills it kills a lot of microbes, and it also kills living plant material. So I wondered, maybe we can use this to our advantage. I hoped that we could kill clover roots with anhydrous ammonia to increase our clover suppression and reduce the costs of management. So I started this experiment. It was a factorial design between the strip tillage tool and the rototiller. And I also had both ammonium nitrate, which is a fertilizer that doesn't result in that caustic zone as much, and then anhydrous ammonia, or both banded under the row at the same nitrogen rate. So they were both applied at the same end rate, but they were two different products, right? And so I was looking at trying to kill clover roots, remember. So I did a lot of sampling. John says that I tend to do that. I should count up how many samples I've taken, but maybe close to 10,000. It's a lot. So anyways, I got to sampling. I used this hammer drill core. Ryan and I were out there using this hammer drill core, and we took 3 cores and composited them. And we collected them in the 0 row zone. This is 1 row width. We took them on the corn row and offset 12, 25, and 38 centimeters relative to the corn row. So we can kind of get a spatial distribution of clover roots over the row and interrow zone in the living mulch system. And I also took them before tillage, after tillage, after fertilizer, and at corn physiological stages, VE, V3, V9, VT, and R4. So that's our spatial component. So I got a spatial and temporal distribution of these root biomass fractions. After I got those samples, it was like 150 pounds of soil every time we brought back. It was a lot. So I mixed those up, homogenized them, and extracted soil nitrogen and collected bulk density from those subsamples. And then I elutrated all the root biomass. So that's basically wash all the soil off of those roots and then dry those out. Spent a lot of time sorting, sifting through those, trying to get all the sand out of the remaining root fractions before we weighed, ball milled, and then we're able to analyze those samples for 13C isotope signature. So we did that because the corn and the clover are C4 and C3 plant respectively. So they have a slightly different photosynthetic pathway. And so they take up different proportions of 13C isotope or the carbon isotopes. So they have a slightly different ratio. And so by analyzing them for that, we were able to determine the relative abundance of corn and clover roots in that bulk sample. And I had some pure corn and pure clover root samples that I used as standards, then mixed them at different proportions. And this is our standard curve. And it has an R squared of 0.997. So if Martin's here, you can be proud of that. Did a lot of work for us on that. So yeah, I was pretty happy with how that worked out. And it kind of made us feel really good about the methods that we were using. So our the spatial distribution that we came up with after we did all that, we found a spatial distribution of our clover root biomass. So this is half subsection of the row and interrow zones in the living mulch system, and it was significant. It was a significant interaction between strip tillage, rotozone tillage, and zone. So they had slightly different distributions, and specifically the rotary zone tillage tool depleted clover roots in that 12 centimeter zone relative to the strip tillage tool. And that kind of makes sense, right? Because it's a little wider working width, and so it mulches and chops up those roots a little more effectively over a wider space. We also got our temporal distribution of clover root biomass, and we see that these both declined. This was also an interaction between our tillage tools and time, and these both declined over the growing season. And what surprised me and what might surprise you is that the rate of the decline is different between these tillage tools, and that didn't really make sense to me because our treatment is applied right here, right? And so the treatment effect widens over time. And that doesn't really make sense just thinking about that conceptually. And so what I think is happening over in this graph is that this is a result of clover root death through tillage and then subsequent mineralization of those biomass pools, and our method's inability to differentiate between living and dead/dying root fractions. So basically this difference right here happened early in the season, but it shows up here. So our rotary zone tillage tool depletes clover roots much more relative to our strip tillage tool. When we look at our corn root biomass, this is our in our different row zones. We see that most of the corn roots are in this 0 centimeter zone. So right on the corn row. And that's not really that surprising either. There's just a few in the 12 centimeter zone and basically none in that interrow zone. So our corn roots are mostly confined to the row zone, and there's only very few that infiltrate that interrow space. That also kind of makes sense because there's a lot of competition in that zone. The clover is probably taking up some moisture. So corn roots don't have any reason to really infiltrate in that zone. And again, we also looked at nitrate concentrations, and this was a little different model than I used in the dissertation, but I think that it points out what the point that I wanted to make, which is the 25 and 38 centimeter zones also increased in nitrate towards the end of the growing season, same as we saw in our 2020 data set when we were looking at soil nitrogen concentrations over time. But again, this is not really enough to account for the biomass inputs from shade suppression. So at the end of the growing season, remember the initial plan for this experiment was to look at our different tillage tools and see if we could come up with similar yields, so that we could reduce our management costs by not having to utilize the Rotary's own tillage tool. And so we didn't have any differences between fertilizer, tillage on grain yields. And so we can conclude from that Rotary's own tillage is not always necessary to maximize grain yields in these systems. So we can optimize our management in other areas and reduce management costs in that way. So in conclusion, no, that was also kind of a lot of information, but there are a lot of clover roots. I said that in the beginning, but there are a lot of clover roots, and we were able to quantify that 10 to 20 tons per hectare. And that's kind of a wide range, but that probably changes over long-term trends too and how we manage it. But there are a large amount of clover root biomass in these systems. Clover roots die from tillage. That also shouldn't be a surprise, but maize roots are confined to the row zone. And because of that, our biomass nitrogen inputs in the interrow are probably not available to our corn. Remember, we saw that response to nitrogen rate despite a ton of nitrogen inputs in that interrow zone. Those roots are spatially separated from where that biomass is being deposited. And we also can conclude that tillage and environmental conditions might interact to predict maize yield. So again, the Rotary's own tillage tool is not a requirement every year, as long as the rest of our management is good, and like the growing season kind of allows that other tool to work better. So they're interacting instead of a requirement for the Rotary's own tillage in every case. So I was able to with that chapter, with the previous chapter, I already defined the spatial temporal biomass inputs, and we kind of gave a little bit more context to the fate of interrow nitrogen inputs. And now we know what's kind of going on underground in this intercropping system. So I'm going to make a jump now to everyone's favorite topic, nitrous oxide, right? Nitrous oxide is, for those who don't think about it every day, sometimes I do. It's a potent greenhouse gas. This is just comparing it to other greenhouse gases. CO2 has a greenhouse gas equivalent of 1 to CO2, and nitrous oxide is about 296 times more powerful of a greenhouse gas than carbon dioxide. And most of the emissions of nitrous oxide actually come from agricultural soil management. So it's a really large issue in corn cropping systems, and sometimes it's overlooked because it's a little bit difficult to measure and quantify its emission. And nitrous oxide is produced through denitrification. Actually, it's a partial denitrification process where we start with nitrite, which is actually an intermediary between nitrification and denitrification. So we start with nitrite, and then under anoxic conditions, denitrifying bacteria utilize the oxygen as an electron acceptor. Then it goes through the denitrification process. And along this process, nitrous oxide can be lost and emitted into the atmosphere. And a lot of times it takes anoxic conditions and a lot of fertilizer and nitrogen inputs to actually spur a lot of denitrification. And so when we look at its data, we often see these spikes in emissions right after rain events. So early in the year, when there's a lot of nitrogen available, after we apply all of our nitrogen inputs to our crop, and the crop isn't, taking up a lot of water. It's not taking, and there's a lot of nitrogen remaining in that soil profile. If we see a rain event, it doesn't take much to produce an anoxic condition at a certain microsite and denitrification processes to begin, and emit a lot of nitrous oxide in a short amount of time. So this is kind of what the data looks like over a growing season, where it returns to kind of a baseline level in the later part of the year. There's been some work looking at, this is a classic paper from Tim Parkin in the 1980s, and he kind of introduced an idea of soil microsites as kind of a source of denitrification variability, right? So what happened in this experiment was there was an incubation of a soil core, and he kept splitting it apart and trying to quantify the different contributors to nitrous oxide emissions. And the results were were surprising when I initially read it, was that a lot of the nitrous oxide emissions actually came from very small pieces of residue or organic matter that were present in the soil core. So there was a beetle carapace and a couple plant roots and a pigweed leaf that were actually contributing to a lot of the nitrous oxide emissions at a very high rate. And so this kind of idea of a hot spot of denitrification activity, where there's a rich substrate and a lot of microbial activity happening in one location, which is utilizing a lot of the oxygen in that immediate area, in that surrounding area. So that metabolism is depleting oxygen and actually can create an anoxic condition where denitrification can then take place. So that's another kind of source of nitrous oxide that is a lot more difficult to model or to predict, right? Because it's at a microsite from a very small portion of plant residue or organic matter, right? And so turning around a little bit, nitrous oxide in a Kura Clover living mulch system, nitrous oxide emissions in the living mulch system, the information is relatively sparse. This is the only real paper that talks about nitrous oxide emissions over an entire growing season. This was from Turner et al. This project was done in Rosemount with some automated chambers, and they looked at the Kura Clover living mulch system relative to conventional in blue. And what they found was that the Kura system, at the end of the growing season, when they integrated all these emissions, they found that the Kura Clover system emitted almost double what's emitted in the conventional system. And actually, a lot of those emissions are contributed at a relatively higher rate at the end of the growing season with kind of an elevated baseline emission. So we see that red line kind of has a greater slope at the end of the growing season. And in this graph too, I think this was a different growing season where there was spikes of emissions towards the end of the growing season. So I kind of looked at this and also looked at Rod and knew that I needed to measure nitrous oxide because it's obviously important and we're interested in that in our lab. And I tried to expand upon it with my previous experiment by sampling row and interrow spaces separately. So I treat those zones kind of disparately in the rest of my experiments. So I kind of wanted to see what the relative contributions that those zones had to nitrous oxide emissions. And so I had these chambers and I sampled them bi-weekly, so twice a week. And I used a syringe and collected the chamber gases after those chambers were placed for a period of time. And then I used linear or restricted quadratic regression of the sample concentration and the sampling time to determine the nitrous oxide flux in that chamber for that date. And what we found at the end, after we calculated all those fluxes and trapezoidally integrated that, so calculated the area under the curve, I found that I found some surprising results, that about 85% of the nitrous oxide emissions were actually coming from the inter-row space. And I also found this very high variance of emissions in the inter-row. So they don't really behave by N rate, and that's kind of to be expected because the inter-row zone didn't receive nitrogen inputs. And the row zone was much lower emissions overall, and scaled a little bit. Maybe we could say that that's scaled with N rate, but yeah, the surprising part is that most of these emissions are coming from the inter-row zone. So we were wondering what's contributing to these emissions. I didn't really have an answer at the time, and so I kind of dug a little bit further and tried to explain why, despite no fertilizer nitrogen application in that zone, there was so much nitrous oxide emissions. And so I conducted a multiple regression analysis. This was in the same year as my project where I described to you my biomass nitrogen inputs. And so I had a lot of other data that I could use to try to explain these emissions. So I used my daily mineralized nitrogen data, my remaining organic N data, standing clover biomass, 3-day cumulative precipitation as kind of a stand-in for soil moisture data. I also utilize air temperature and nitrate and ammonium concentrations. And I did this multiple regression analysis, was able to explain 20 and 16% of the variance of these emissions. So not really great in some respects, but for nitrous oxide, it's inherently variable thing. So so it worked out. So we were able to explain some of the variance at least. And what we found was that precip and nitrate concentration were significant in 2020. And that's kind of what we see with a lot of nitrous oxide emissions data. When I was telling you about the conditions required for denitrification, wet and fertilizer or soil nitrogen resources available in that zone. So those were significant for both the row and the inter-row. And in the inter-row, we also found that standing clover biomass was also a significant contributor. So, you know, when I was thinking back about this and all the times I went out there to sample nitrous oxide, I remember getting my feet wet. And I remember that humid zone under that clover canopy that's created after dew or after a rainfall. And so I know that that's a really rich zone of biology, right? And it's a really, it's really optimal conditions for a hotspot to form. And so, you know, my hypothesis is that this biology that's happening right here and all these little pieces of residue, you know, it wouldn't take much for a hotspot to form and nitrous oxide emissions to be elevated because of all those biomass inputs. So, so that's what I found. So the unintended consequences of the living mulch system. I understand that this was 1 year of nitrous oxide data. I have another year, but there was different drivers because of the extreme drought. So I understand that the hotspot theory should be tested further. But if this is confirmed and this is true, mitigation efforts might be difficult, because how do we stop microbial processes from happening when we're adding 3,000-4,000 kilograms of clover biomass inputs every year, right? And also, these high emissions. I guess I didn't give some of that context. These emissions that I found, it was about 3.4 kilograms per hectare. That's about double what we like to see, or what we typically see in a conventional corn cropping system. And so that offsets, because it's 296 times more potent than CO2 as a greenhouse gas, that can offset some of the conservation benefits that initially got us excited about this cropping system. So I know it's a downer. So overall, what we found over the last 3 years is that nitrogen credits are probably not from above ground biomass pools. And what I think is more likely is that the root biomass that's disturbed through tillage and the subsequent mineralization contributes to a lot of the nitrogen inputs in this system. So it's probably like a longer term effect between like rotation management and clover stand health at the time that we put our corn in there. So, and we also found that, or confirmed from the Turner paper, that these systems do emit an alarmingly high amount of nitrous oxide. And if my theory is true, these hotspots make mitigation efforts that much more difficult. So, I mean, there might be some residue management things that we could do, like harvesting some of that clover residue. Since it's not really useful to us, it's not going to that corn crop anyway. So there might be some things that we could do, but there's definitely some opportunities for some more work. So, thank you all. I really appreciate the support today. And I want to thank John, giving me the opportunity initially, and being by my side over the 5 years. That was best experience. So couldn't have been better. Also want to thank Rod, my co-advisor too, who mentored me, got me thinking about these complex issues. Of course, Holly, I didn't have her picture, so I didn't put her in here either, but she kind of got me started down this road too. And also my original advisor, my dad, who's back here too. What year was this? Yeah, so of course a lot of other people. Bill helped me out there in the field too. Got a snapshot of him my first year. So Ryan helped me sample all those root biomass samples and hucked them back to campus. Jerry manages my plots, expert at that. And then of course all the rest too have helped me throughout this process. I know it's not a one-person show. So Josh, Kurt, Scott, Martin, Forrest, etc. George elucidated all those samples. That was an incredible effort. And then of course Caitlin too. I had to do some of this stuff in our apartment during the pandemic. So I was like preparing field stuff and everything. So she helped me out there. So yeah, these are my supporters, and found this guy in the field too. He thinks I'm a gopher. We were friends. So that's all.
Questions now?
John, nice presentation. I thought you were worried about soil erosion and you eroded a whole bunch of soil by you creating all those roots. So one of the questions I have is, between your thesis, your master's thesis and your dissertation now, your master's, you say, well, Kura is going to support corn production. It's giving us a lot of nitrogen. We don't need to apply as much nitrogen. Now you're seeing that that's not necessarily the case. Can you tell us a little bit maybe what you think changed between kind of your earlier work versus this current work?
Right. So yeah, the results that we got from these two experiments were very different. They were both conducted in Rosemount, but they were conducted in different field sites. My thesis was on a really nice piece of ground that was established in 2006. and it was used a lot for row crops and had kind of a pretty extensive cropping history. But it had a year or maybe 2 years of rest before those experiments were initiated. And I do think that managing the living mulch system long term is depleting those corn or those clover root fractions. And eventually, once those biomass pools are gone, they're not mineralizing and giving us the benefit. So the site that I was on for this experiment was a little newer established field. And so it maybe didn't have as established of a root system, or it maybe had a more intensive cropping history. So
That was thanks to our former dean, who sold off the mineral rights to have the state forced us to decidedly inferior as well.
And I got a question for you.
yeah, of course.
Rosemont has about 2.5 feet of soil and 20 of rock. And you quantified what's going in the plant and nitrous oxide emission. If you add 86 pounds of nitrogen from the grower and 180 from the fertilizer, that's a lot of fertilizer. And if you get rains, it's going to leach. And you didn't make that component, and that's a major part that we worried. So basically, you have gone through it without saying it, that this system may not work. Is that what you're saying?
It's true. I didn't quantify nitrate leaching. There was some work previously that did quantify nitrate leaching, and they did find that it reduced it relative to conventional management. One thing is that a lot of the nitrogen inputs are actually towards the later part of the growing season, and so our soil profile is going to be more depleted from moisture, and so hopefully there's not as much vertical transport of nitrate in August as there is, in the early part of the year. I see you looking at me.
Based on the river data that we looked at it, when nitrogen goes, we are not worried about in the fall because the soils are empty.
Right.
For water, and so it stores it, and next spring it's going to leach.
Right.
So we didn't go to that step.
Right.
So we cannot make that claim.
Well, that's true. I don't know the exact details of the study that did look at leaching in this cropping system, and I'm going to be working on my postdoc too, and we're going to be measuring some more of that stuff. But yeah, I wonder if those nitrogen deposits happen in the later part of the year, but we actually didn't see it in the soil mineral pool. And so I wonder if some of that is actually being recycled immediately by that large amount of clover root biomass. And also towards the end of the year and the next spring, that flush of growth is potentially taking some of that up. Those are questions I don't know, but that's just my conceptual understanding of it. So it's going to be hard for me to argue one way or another. Carl.
Yeah, I got a question. Nice job, John, and a lot of unintended consequences. One other one might be, I don't know if you thought about this, is all focused on nitrogen, but what about phosphorus in this system? Because you're going to have a lot of residue on the surface. You show that it dies. If you have runoff, obviously you probably get less sediment, but you might have more dissolved phosphorus. So I don't know if anybody's looked at that.
Yeah, I've not looked at phosphorus, but the one thing that comes to my mind is we've measured infiltration in these systems, and John has some work that shows we increase infiltration by about 10 times. And that's why when John did that erosion work early on, that was on a pretty steep hill slope, right? And they found basically negligible soil erosion from rills. And so I wouldn't expect that there would be a lot of surface runoff to carry that orthophosphate.
During the growing season, but if the soil freezes.
Oh.
During that time.
Right.
Snow melt and things like
that. Okay. Yeah, that would be an interesting thing to look at.
Something to look at.
Always, right?
How does the carbon budget stack up against the night? Like, so, you know, I mean, presumably we've got more primary productivity here. There's some credit for that going in the soil. Is that acts to counterbalance the stock side?
You know, of course, right. There is additional biomass in the system. I mean, it depends on how it's managed too, right? Like, if the living mulch actually does suppress yields, then corn yields, then that could actually take away from the carbon uptake in this system. So that's an entire research program of itself, is trying to quantify the carbon budget of this. You know, and that just offsetting some of those additional emissions. That kind of brings me to another idea that I was thinking about earlier, is that cover crops actually provide some albedo. And there's some data or there's some literature out there that describes that that increased surface albedo does also reduce some of the warming potential out here too. So that's another piece that that could go into the offset portion. So relative to flat ground. So yeah, there definitely are some things to look at in that, but no, I would have no idea what our carbon budget would look like relative to our nitrous oxide emissions.
John, you alluded, several times that 2021 did not go as anticipated because of the drought. So out of that data, and I know, for several of these, you didn't present that data, but what did you learn from that might be important as we think about shifting climate and climate change and more extreme weather on either end of the spectrum, whether it be intense drought or intense precipitation events? What can you say about this system from that particular year?
Right. That's a really good point. And I wish I had some more time that I could have described some of those studies. I had one study in Arlington, Wisconsin, and I replicated that experiment in Rosemount just in 2021. And we had severe and moderate drought conditions at those locations. And so I was intending to use that as kind of like a row establishment. So I had like banded herbicides and a couple different row establishment tools and nitrogen rates as well. And I hope to kind of use that experiment to see if there were differences in like optimal nitrogen rates because of like differences in tillage and incorporation, right? But what we found, because I framed it around the drought and found that the banded herbicides actually out yielded the tillage treatments in Rosemount, whereas the Rotary's own tillage tool out yielded the banded herbicides in Arlington. And so there were different moisture conditions at those different sites in the spring. And so banded herbicides I found was able to conserve some moisture in the early part of the year so that those seedlings could grow and develop normally or more normally. And then tillage is actually more optimal when we have wet growing seasons. Another point I want to bring up. So there's some management things that we can do to increase the water conservation. And so that can be a little bit of an adaptive management practice that I was talking about, where we're kind of taking in information at the moment and trying to and looking at forecasts and seeing if we can optimize things that way. But also the water management aspect for like extreme rain events is something that's really interesting to me because of that high infiltration. I wonder if this was on a field scale, if we had a 6-inch rain, if it would be more well dispersed over the landscape instead of having surface runoff and a hillside like problems with too moist conditions. So I wonder if the Clover system can be a water management tool in that way, but also recognize that it could lead to severe or more severe moisture stress in the spring too, but we might have some management practices that could respond to that.
Is there anything in the chat? Questions?
I'm just getting congrats, so. So.
Any further questions before we adjourn? Maybe the minutes. Now let's give John a hand.
Yep.
Let's start at 11:15, I guess, in S4:15 committee.
Thanks, everybody. Really appreciate it. Thanks, everyone on the chat.
Yeah.